All right, let's explore. Number 10. The twin paradox. In 1905, Albert Einstein published his special theory of relativity, and embedded within its equations a conclusion so strange that physicists are still grappling with its implications today. Two identical twins, one remaining on Earth and one traveling into space at near the speed of light, would age at measurably different rates. When the traveler returned, they would be physically, biologically younger than the sibling they had left behind. Not metaphorically younger, actually younger. This wasn't a thought experiment designed to be dismissed. In October 1971, physicists Joseph Haffel and Richard Keating placed extremely precise atomic clocks aboard commercial aircraft and flew them around the world. When the airborne clocks were compared to identical clocks that had remained stationary, the differences were exactly what Einstein's equations predicted. Clocks on eastward flights lost approximately 59 nanoseconds. Clocks on westward flights gained approximately 273 nanoseconds. Time had physically passed at different rates for each clock. The implications reach into everyday life in ways most people never consider. The GPS satellites orbiting Earth move fast enough and exist in a different gravitational environment, sufficiently distinct from the surface that their onboard clocks drift by roughly 7 microseconds every single day relative to clocks on the ground. Without daily corrections accounting for relativistic time dilation, GPS navigation would become useless within minutes. The engineering of modern civilization depends on accepting that time does not flow at a single universal speed. French physicist Paul Langevin formalized the paradox in 1911, and it has never been resolved in any philosophically satisfying way. At 99.9% of the speed of light, 1 year of travel corresponds to approximately 22 years passing on Earth. Both clocks are correct. Both twins' experiences are equally valid. Time simply runs at the rate your velocity and gravitational environment dictate. Time is not a river flowing at one fixed speed beneath everything. It is a substance that stretches and compresses, depending on where you are and how fast you are moving. And nothing in physics explains why there should be a real rate at all. Number 9. The grandfather paradox. In 1943, French writer René Barjavel published a novel called Le Voyageur Imprudent and posed a question that has since migrated from science fiction directly into the working papers of theoretical physicists. What happens if a time traveler goes back in time and kills their own grandfather before their parent is born? The traveler could never have existed. But if they never existed, they could never have committed the act. If the act was never committed, the grandfather survives, the traveler is born, and the whole sequence begins again. For most of the 20th century, physicists were comfortable dismissing this as a purely fictional problem, since general relativity appeared to forbid the kind of time travel required. Then, in 1949, mathematician Kurt Gödel proved otherwise. Working from Einstein's own field equations, Gödel produced a solution describing a rotating universe in which closed time-like curves, paths through spacetime that loop back to their own starting point, were mathematically permitted. He presented his findings to Einstein personally. By all biographical accounts, Einstein found the result deeply troubling. The grandfather paradox immediately became a genuine crisis. If the geometry of spacetime can contain loops, then causal contradictions are not just imaginable. They are physically allowable structures within our best theory of gravity. In 1992, Stephen Hawking proposed what he called the chronology protection conjecture, the idea that some unknown mechanism within physics conspires to prevent closed time-like curves from forming, specifically to avoid paradoxes of this kind. It was an elegant proposal. It remains completely unproven. Soviet physicist Igor Novikov offered an alternative in the 1980s, the self-consistency principle, arguing that any events occurring within a closed time-like curve must be mutually consistent. Paradoxes cannot occur, only loops that resolve without contradiction. The traveler's actions were always part of history. Nothing can be changed because everything that happens is already what happened. We don't have a confirmed law of physics preventing time travel. We have a conjecture, an educated guess dressed in mathematical language, standing between our best theory of space-time and logical impossibility. Number 8. The bootstrap paradox. In October 1941, science fiction writer Robert Heinlein published a short story called By His Bootstraps in Astounding Science Fiction magazine, and in doing so named a problem that physicists would eventually be forced to take seriously. Imagine a time traveler who goes back and gives Isaac Newton the complete equations of calculus. Newton publishes them. They survive through centuries of mathematics, and eventually they reach the traveler who carries them back. Newton discovered calculus. The traveler provided it. The information was created by no one. It simply exists, cycling through time with no point of origin. Physicists call this the ontological paradox. Unlike the grandfather paradox, it doesn't destroy a timeline. It does something arguably stranger. It permits information, knowledge, even physical objects to exist in a closed loop with no origin point, no creator, no moment of first invention. The content simply is perpetually self-referencing, causally untethered from any beginning. In 1988, physicist Kip Thorne and colleagues Morris and Yurtsever published a paper in Physical Review Letters, demonstrating that traversable wormholes, if they could be constructed, would share the same mathematical framework as closed time-like curves, and would therefore permit informational loops of exactly this kind. The paper was not fringe speculation. It appeared in one of physics' most prestigious journals, and opened 2 decades of serious academic discussion about whether causality is a fundamental law or merely a useful approximation. No proposed solution to the bootstrap paradox has achieved anything approaching consensus. The problem is not that we lack answers. The problem is that the answers we have require dismantling assumptions so basic we rarely think of them as assumptions at all, that every effect has a prior cause, that information must be created before it can exist, that the universe keeps track of where things come from. If time travel is physically possible, then causality is not a law. It is a habit, and the universe has no obligation to maintain it. Number 7. Zeno's paradoxes of motion. Around 450 BCE, Greek philosopher Zeno of Elea constructed a series of arguments designed to prove that motion is logically impossible. The most devastating of these, preserved by Aristotle in physics, concerns an arrow in flight. At any single instant, the arrow occupies exactly one position in space. It is not moving. It is simply there, frozen in a specific location for the duration of that moment. If every instant of the arrow's flight is a moment in which it is stationary, Zeno asked, how does it ever move? How does time advance through a succession of frozen nows? For 2,000 years, this was treated as a clever sophism, a trick of language, rather than a genuine problem. Then, in the 1660s and 1680s, Newton and Leibniz independently developed calculus, providing mathematical tools that could sum an infinite series of infinitely small intervals and arrive at a finite result. The arrow travels a measurable distance. The mathematics works. Problem solved, or so it seemed. The trouble is that calculus describes what happens. It does not explain why. It tells us that an infinite series of instants converges to a finite time, but it says nothing about the physical mechanism by which one frozen moment transitions into the next. What actually occurs inside a single instant to produce motion? The mathematics skips over that question entirely by treating time as a continuous variable, which is precisely the assumption Zeno was challenging. Modern physics has reopened the wound. Max Planck's 1900 work on quantum theory introduced the possibility that time itself may be discrete rather than continuous, composed of irreducible units. The Planck time, approximately 5.39 times 10 to the negative 44 seconds, represents the theorized smallest meaningful interval. If time is granular, Zeno's arrow paradox reemerges at the quantum scale. Between any two adjacent moments, there is no intermediate state. The transition itself has no duration and no mechanism. Zeno did not fail to understand motion. He may have understood it more clearly than anyone who came after him, because the mechanism by which the present becomes the past has never, in 2,500 years, been satisfactorily explained. Number 6. The quantum Zeno effect. In 1977, physicists E.C. George Sudarshan and Baidyanath Misra published a paper in the Journal of Mathematical Physics that turned an ancient philosophical paradox into an experimentally testable prediction. Named deliberately for Zeno of Elea, their finding was this: an unstable quantum particle that is continuously observed will never decay. Watching it, in the most literal physical sense, freezes it in time. Observation does not merely record what happens. It prevents what would otherwise inevitably occur. This sounds metaphorical. It is not. In 1990, physicist Wayne Itano and colleagues at the National Institute of Standards and Technology confirmed the effect experimentally using trapped beryllium ions. They repeatedly measured the quantum state of the ions at carefully controlled intervals and found that the more frequently they measured, the more the decay was suppressed. The act of measurement itself, of collapsing the system's quantum wave function back to its initial state, reset the probability of decay. At sufficient measurement frequency, decay halted entirely. The mechanism is now well understood within quantum theory and has since been observed in cold atoms, quantum dots, and nitrogen vacancy centers in diamonds. There is also an anti-Zeno effect, confirmed experimentally, in which measurements at certain intervals actively accelerate decay rather than suppress it. Time's passage for a quantum system is not a background condition independent of observation. It is a variable that changes depending on whether the system is being watched. The implications are not confined to laboratory particles. If time's progression depends on observation at the quantum level, then an unobserved universe would behave differently than one containing observers. This is not a philosophical speculation. It is a prediction that follows directly from the mathematics of quantum mechanics. If time only passes for things that are being watched, then the vast majority of the universe, everything that has never been observed and never will be, may be experiencing time in a way that bears no resemblance to what we measure in any laboratory on Earth. Number 5. The information paradox. In 1974, Stephen Hawking published a paper in Nature titled Black Hole Explosions and demonstrated mathematically that black holes are not truly black. They emit thermal radiation, now called Hawking radiation, and over vast timescales they lose mass and eventually evaporate entirely. The scientific community celebrated. Then Hawking himself realized what his own discovery implied, and the celebration became one of the deepest crises in modern physics. Quantum mechanics rests on a foundational principle called unitarity. Information is always conserved. It can be scrambled, compressed, or redistributed, but it can never be genuinely destroyed. Every piece of information about every object that has ever existed is, in principle, encoded somewhere in the state of the universe. General relativity, meanwhile, is equally insistent that anything crossing a black hole's event horizon is causally disconnected from the outside universe. Nothing, including information, can escape. When Hawking radiation carries away all of a black hole's mass, the black hole is gone. And if general relativity is correct, every piece of information about everything that ever fell goes with it, permanently, irreversibly, which is precisely what quantum mechanics says is physically impossible. In 1997, Hawking famously bet physicists Kip Thorne and John Preskill that information was truly destroyed. He conceded the bet in 2004 at a conference in Dublin, reversing his position. But conceding the bet didn't resolve the paradox. In 2012, physicists Almheri, Marolf, Polchinski, and Sully published what became known as the firewall paradox, showing that every proposed resolution to the information problem creates a new crisis. Saving quantum mechanics from black holes requires a wall of effectively infinite energy at the event horizon, which directly contradicts general relativity's prediction that an infalling observer would notice nothing unusual when crossing it. Both theories cannot be simultaneously correct, and we have no replacement for either. Somewhere at the edge of a black hole, either information dies or our understanding of space-time does, and physics is currently unable to determine which. Number 4. The arrow of time. In 1872, Austrian physicist Ludwig Boltzmann published his H-theorem, an attempt to solve a problem that seemed like it should have been straightforward. Every fundamental law of physics, from Newton's mechanics to Maxwell's electromagnetism to quantum field theory, works equally well in both directions of time. Run the equations forward, run them backward. Physics permits both without preference. Yet something about reality is unmistakably, profoundly directional. Eggs break. They do not unbreak. Heat flows from hot objects to cold ones. It does not spontaneously reverse. The past is different from the future in ways that feel absolute. Boltzmann wanted to know why. He found his answer in statistics. The second law of thermodynamics states that entropy, the measure of disorder in a system, always increases over time. This is not because the laws of physics demand it at the individual particle level. It is because there are vastly more disordered states than ordered ones, and a system moving randomly through its possible configurations will almost certainly move toward greater disorder simply because there are more disordered places to be. Time's arrow, in Boltzmann's framework, is not a fundamental law. It is an overwhelming statistical tendency. His peers attacked the result immediately. Joseph Loschmidt pointed out in 1876 that if the laws governing individual particles are reversible, then any sequence of events leading to greater entropy could, in principle, run in reverse toward lower entropy. Ernst Zermelo raised a related objection in 1896. The professional attacks on Boltzmann's work were relentless and, by biographical accounts, contributed to the deterioration of his mental health. He died by suicide in 1906. The debate he started has never fully ended. The standard model of particle physics confirms what Boltzmann suspected. At the fundamental level, the laws governing particles are time-symmetric. The weak nuclear force exhibits a slight asymmetry called CP violation, discovered experimentally in 1964 by Cronin and Fitch, for which they received the Nobel Prize in 1980. But this asymmetry is far too small to account for the full directionality of time as we experience it. Physicist Sean Carroll at Caltech and others have argued that time's arrow may trace back to the extraordinarily low entropy initial conditions of the Big Bang. But why the universe began in such a highly ordered state remains completely unexplained. There is no law of physics that requires the past to come before the future. The reason your life moves in one direction and not the other is a question that has occupied the greatest minds in physics for over 150 years, and we are not meaningfully closer to an answer than Boltzmann was when he first asked it. Number 3. The block universe. In September 1908, mathematician Hermann Minkowski delivered a lecture in Cologne that would permanently alter how physicists understand the nature of time. Working from Albert Einstein's special relativity, published 3 years earlier, Minkowski demonstrated that space and time are not separate entities. They are a single, unified, four-dimensional structure, now called spacetime. The consequences of this unification are still being absorbed more than a century later, because if spacetime is a four-dimensional structure, then within that structure, nothing moves. Nothing flows. Everything simply exists. This is the block universe, also called eternalism, and it is not a philosophical preference. It is what the mathematics of spacetime geometry most naturally implies. Einstein's special relativity contains a feature called the relativity of simultaneity. Two observers moving relative to each other will genuinely, irreconcilably disagree about which events are happening at the same time. There is no experiment either can perform to resolve their disagreement. Neither is wrong. This means there is no universal now connecting all observers. If now is not a shared physical fact, then the present moment is not objectively special. Past, present, and future exist with equal reality, equally permanent, equally fixed within the block. Physicist Brian Greene explored this interpretation extensively in his 2004 book, The Fabric of the Cosmos. And physicist Julian Barber argued even more radically in his 1999 work, The End of Time. That time does not exist at all, only a static configuration space of frozen nows, each equally real, none more present than any other. These are not fringe positions. They represent the interpretation of spacetime most consistent with our best physical theories, held by many, though not all physicists. If the block universe is correct, your experience of time passing, of moving from moment to moment, of having a past behind you and a future ahead, is a perceptual artifact of your position within a four-dimensional structure that does not itself change. Every moment of your life exists simultaneously, frozen into the geometry of space-time. The you that existed 10 years ago is as present as the you reading this sentence. Death is not an ending. It is simply a location further along the fourth dimension, permanent and unchanging. According to our best physical theory of spacetime, you are not moving through your life. You are a static four-dimensional object, already complete, every moment of your existence simultaneously present within the geometry of the universe, and the feeling that time is passing may be the most universal and most total illusion that has ever existed. Number 2. The Boltzmann brain paradox. In 1895, Ludwig Boltzmann, confronting the implications of his own statistical mechanics, raised an idea as a reductio ad absurdum, a consequence so absurd it was meant to expose a flaw in the opposing argument. If the universe operates on statistical principles over a sufficiently long timescale, random fluctuations in entropy will inevitably produce configurations of arbitrarily complex order, purely by chance. In principle, a fluctuation could produce a fully formed, self-aware brain, complete with an entire set of false memories of a past that never occurred. Boltzmann intended this as a thought experiment to be rejected. In 2004, physicists Andreas Albrecht and Lorenzo Sorbo published a paper in Physical Review D, demonstrating it could not be so easily dismissed. The problem is statistical. In an eternal or sufficiently large universe, Boltzmann brains, self-aware structures arising spontaneously from random thermodynamic fluctuations, will inevitably appear. More than that, they will appear with vastly greater frequency than observers who arise through the long, slow process of cosmic evolution, stellar formation, planetary chemistry, and biological development. In any universe large enough to contain Boltzmann brains at all, genuine observers of the kind we believe ourselves to be would be extraordinarily rare by comparison. The mathematics implies that in such a universe, you are statistically far more likely to be a Boltzmann brain than a human being with a genuine past. Physicists Andre Linde, Sean Carroll, and others have written about this problem in peer-reviewed journals, not as a curiosity, but as a genuine threat to the foundations of cosmological reasoning. The difficulty is that there is no internal evidence available to a Boltzmann brain that distinguishes its experience from that of a genuine observer. Every memory, every sensation, every scientific measurement it believes itself to have made is a product of the fluctuation. None of it tracks reality, which means that if the probability calculus is correct and you are more likely to be a Boltzmann brain than a genuine observer, then every piece of data you think you have collected about the universe is potentially unreliable. This is not merely an unsettling philosophical possibility. It is a direct attack on the legitimacy of scientific inquiry itself. If Boltzmann brains are statistically dominant, then any observation any scientist has ever recorded, any experiment ever performed, any measurement ever taken could be the false memory of a mind that spontaneously appeared 2 seconds ago and will dissolve just as quickly. The entire edifice of human knowledge rests on the assumption that our observations correspond to a real external world with a genuine history. The Boltzmann brain paradox does not merely challenge our understanding of time. It challenges our ability to trust any information time has apparently delivered to us, which means the paradox you're about to hear is one that undermines even the tools we would use to investigate it. Number 1. The matter-antimatter asymmetry. At the moment of the Big Bang, 13.8 billion years ago, the laws of physics as we understand them required that matter and antimatter be created in exactly equal quantities. Every particle produced by the initial expansion of the universe should have been paired with a corresponding antiparticle of opposite charge. When matter and antimatter meet, they annihilate each other completely, converting entirely to energy. A universe born with perfect symmetry between the two should have spent its first second destroying itself, particle by antiparticle, until nothing remained. No matter. No atoms, no stars, no planets, no chemistry, no biology. A universe of pure, structure-free energy in which nothing could ever happen, and no one would ever be present to notice. In 1967, Soviet physicist Andrei Sakharov outlined the 3 conditions that would need to be satisfied for a slight excess of matter over antimatter to develop, allowing some residue of matter to survive the mutual annihilation. His conditions included violation of what physicists call CP symmetry, the combined symmetry of charge and spatial reflection, one of the most fundamental symmetries in the Standard Model. In 1964, physicists James Cronin and Val Fitch detected exactly such a violation in the decay of particles called kaons. The discovery was real enough to earn the Nobel Prize in Physics in 1980. In 2001, both the Babar experiment at SLAC and the Bell experiment at KEK in Japan independently confirmed CP violation in the decay of B mesons. The asymmetry exists. Physics is not perfectly time-symmetric after all. Here is the problem. The measured degree of CP violation in the Standard Model is approximately 10 billion times too small to account for the matter-antimatter asymmetry we observe. The amount of symmetry breaking actually detected in particle physics experiments could not have produced a universe with enough leftover matter to form a single galaxy, let alone the hundreds of billions we can see. In 2017, the BASE collaboration at CERN measured the magnetic moments of protons and antiprotons to a precision of 0.3 parts per billion and found no measurable difference. Every precision test we conduct narrows the window within which new physics could hide, and yet the asymmetry that produced everything remains without a confirmed explanation. The surviving excess of matter over antimatter was approximately 1 particle per 1 billion matter-antimatter pairs. That ratio is everything. Every star, every planet, every ocean, every atom of every living thing in the observable universe is the residue of that 1 in a billion surplus. Physics cannot explain where it came from. The Standard Model predicts an asymmetry 10 billion times too small. Every proposed extension of the Standard Model, every attempt to find new sources of CP violation at particle accelerators, has so far failed to close the gap. The problem is not that we have no theories. The problem is that our best theories, tested with the greatest precision instruments humanity has ever built, consistently confirm that the universe we live in should not exist. You are here because of a violation of time symmetry so slight that physics cannot account for it, in a universe that should have annihilated itself before a single second of cosmic history elapsed, composed of matter whose survival cannot be explained by any confirmed law, observed by a mind whose reliability the Boltzmann brain paradox calls into question. moving through time whose direction has no fundamental basis, embedded in a space-time block where every moment you have ever lived is simultaneously present and permanent. Physics does not know why you exist. It can only confirm with extraordinary precision that you do. If you want to see more videos like this, click the video on screen now and make sure to subscribe.